picking up. Should I scoot her over a little bit?
No, it's okay.
You should scoot her onto the screen to help you teach.
And I hope Ava is okay.
She's doing fine. She's watching. I don't know. YouTube is. I'll have to peek over. Just make sure she doesn't end up somewhere bad. Most of it's just really mindless kids songs. Coco Melon's becoming a favorite in our house. Um, Dan nodding. He gets it. Uh, but it's amazing when she's on the tablet, just how much it's just like click, 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 click. Like she won't sit through things. Um, but yeah, she should be good for a bit, an hour and a half, maybe not. But I might take a little break here when we go to breakout groups or breakout group, I guess. So I changed a bit what we're talking about today. I had originally said we were going to do alternative data structures, so XML and JSON. It's too programmy to get into in our last lecture. There's too much in terms of the libraries. So the main library for parsing XML is called capital X, capital M, capital L. In R, and it works well. I use it, but it very much takes like a computer programming approach to programming, and I just didn't want to get into that. The other thing I had always been thinking about was ending on machine learning, so I'm going to go over how to do classification trees. And within that, we'll cover a bunch of the other kind of machine learning approaches that we don't necessarily do all the time in statistics, or maybe you do and I just didn't cover. So R is really one of the premier languages being used in machine learning. Now the other is Python, and Python probably is more popular. And as well, there are like Amazon Web Services has their own kind of programming interface, and there are some Bayesian methods that are relevant. But R certainly is amongst the top. When I taught a data mining course a couple of years ago to the health informatics students, I taught it with R, and it can handle all the machine learning you would do. The place that really starts falling apart is in the really complex, like deep learning, multi-level neural networks, or if you really want to dive into the guts of a neural network, that's where you really should be transitioning to Python. But for everything else, all the clustering and basic classification, R can support it. So I'll talk a little bit about training and test data, and then building, presenting, and evaluating classification and regression trees, what we're talking about. Though most of what we're doing here would be applicable to other classification methods as well. So what are some of the other ones we use? Naive Bayes classifiers, neural nets, random forests, gradient boosting, and add a boost are all implemented in R if you're interested. But CART it's the easiest. It's also my favorite because I like the visualizations. So when we're doing machine learning, and particularly with the classification methods in machine learning, we're primarily interested in the accuracy of the prediction, which is rarely our primary concern in statistics, right? We care if we predicted the outcome well. That's why we have things like R squared, or we look at the log likelihood in logistic regression, but that's not our primary concern in statistics. Isn't whether we predict it, whether y hat is close to y. Our primary concern is how the beta hats influence the y hat, right? Our primary concern in statistics is how the variables we put in the model predicted our outcome. And that's a very different tact in machine learning, where machine learning is primarily interested in how close y hat is to y, right? How close what we predicted is to what we were trying to predict. And different machine learning algorithms do a better or worse job of explaining what part or how much of the model is used in the final result. So classification trees actually do provide a bit of an explanation about predicting y with your x's. Naive Bayes classifiers use a little less, and then when you get to the complex one, random forests, there's some interesting work on extracting meaning out of random forests, but the ensemble methods don't explain things well. Neural networks as well. It's really hard to know if you feed a bunch of data into a neural network and you get a predicted y value. It's hard to decipher how those x's influence the y. So, like, we can't explain what changes in age result in your predicted probability of smoking. All I can tell you is that based on your profile, this is your predicted probability, and I don't have a good explanation for why. So, but if you're in a situation where you care mostly about predictive accuracy, imputation's a great example, where we really don't care how the sausage is made, right? We just want replaced values that are as accurate as possible. That's where machine learning can really be valuable. So one thing we do because of that, because we're really interested in the accuracy of our predictions, we need to test fairly. And in statistics, we almost never do this, right? I don't know how many of you ever, for your statistical models, split training and test and evaluate your model on the test, because we don't, that's not what we're interested in. But if I'm going to be building a model and then evaluating how accurate it is, I shouldn't test its accuracy on the data I trained on, because that will lead to an iterative process where I have a model that's really good at predicting that data set and not the general data. So what we do is we take our big data set and we split it in some way, and we train on one and then test on everything we didn't train on. Now, depending on the size of your data, there are a bunch of different approaches here. So I'm not going to explore things like cross-validation or bootstrapping, bagging and boosting. These are all, in reality, really complicated ways to do a training and a test split. I'm just going to take a random sample. Was it random? No, it wasn't even random. I just took the first 70% of observations and made them the training set, and the last 30% and made them the test set. I actually wouldn't recommend that for production research. You know, you should take a random sample of 70% rather than the first 70%, just because the data might, if there's any kind of pattern in the organization of your data, you would be incorporating that into your training and test model. The advantage for this from a teaching perspective is that I know you'll all end up with the same data set, right? So if I take the first 70% of the observations as the training, then we will all have the same training set rather than doing it randomly. So new data set. Briefly, the behavioral risk factor surveillance system is, and this is a quote from them, America's premier system of health-related telephone surveys. I'm not going to get into it a lot. It's got a bunch of binary values and one continuous variable. So you can follow this link if you, I didn't check to make sure this still works. I should have. Yeah, it's still up. All right. So I pulled the data from Connecticut, because it is the largest small state that gave us a data set that ran quickly in R. R can support large data, but it starts to chug as okay, I tried doing this. The first time I did this, I tried picking California, and it was a minute or two per model, which is fine, but like, if you're learning and running models hundreds of times, you don't want to delay. So we stuck with Connecticut because it's small. So on to classification trees themselves. So it's a little bigger. Classification and regression trees are often shortened to CART. So the idea is, we call them classification and regression trees because they can work on either categorical outcomes, which are typically binary but don't have to be, or continuous. So if they're categorical, they're a classification tree. If they're numbers, if they're continuous, they're a regression tree. The original algorithm has been copyrighted, so that's why, sorry, just one second. I think she opened my Facebook somehow.
Nice.
I didn't know how she did that. So because the CART algorithm is copyrighted, it was rewritten. And this is one of the weird areas of algorithm copyright, where there's another type of classification tree called C4.5, which is a similar approach, uses different algorithms, but it's basically the same idea. It's also copyrighted, so it also has an open source alternative, which is the same algorithm, right? You can't copyright the idea because they published it. So someone has basically just rewritten it. And that's what rpart is. So rpart is the algorithm we're going to use in R. It stands for recursive partitioning and regression trees. And it's just an implementation of the CART algorithm that is free for use. I've never used the CART algorithm. I've never known anyone to pay for it. So rpart is just the one that everyone uses. So the idea is to create this decision tree, a flowchart like structure. And I wanted to pull up an old lecture. So the idea is that we start, I don't have an unmarked up version. So the idea is we start with everything at the top node, and based on a decision rule, we either move people. So this asks if people have arthritis. If they do, we send them this way. If they don't, we send them this way. If they end a determinist, that means that's where the decision is made. And but we can also do splitting. So if they don't have arthritis, we ask if they have diabetes. If they don't have diabetes, we ask if they have coronary heart disease. If they don't have that, then they end up here. At each node, we come up with some sort of evaluation to see, and I'll talk about what the results of the trees are later. We look at how do we classify everyone that got to this node. So important components of the algorithm that I won't cover in detail is like, how do you decide what splits to consider, right? How do you decide what variables to consider at each node? How do you choose the best split? So like, why was that first split on arthritis? And then how do you decide to stop? Like, why did I stop at arthritis? Yes. Why didn't I split on coronary heart disease after that? That's all built into the algorithm automatically, so you don't have to stress too much about that. I'm going to focus more on the equation itself. So the function is called rpart, and if you look at it, it looks very much like a regression model where we have the name of the function, but there's a formula that show. Did I use this tilde dot notation yet? I can't remember if I used it. So the idea of tilde dot is everything else. So here I'm going to predict high blood pressure with everything else in the training data set. So if you look at the training data set, oops. Sorry, I hadn't actually read anything yet. Or I did, and then I had to restart R. So if we look at training data set, there are 13 columns and about 5,000 rows. High blood pressure is a variable we're predicting. And then there are a bunch of yes/no variables. Depression, kidney, and diabetes are also here. They just ran out of space. And there's also a variable called doctor visits. Doctor visits is just the number of times they've been to a doctor. So most of them are binary, and doctor visits is a long tail. Like you can imagine a fairly skewed variable counted the number of times someone has been to a doctor. Can't remember if there are a lot of zeros. I don't think there are. Yeah, so the 375 for a 0 doesn't seem like it's necessarily 0 inflated. It probably, if I messed with the histogram enough, I could probably get it to fit where I could convince myself it's a Poisson distribution with a mean in the 2 to 5 range.
76.
Sorry?
That's a lot at 76.
Yeah. You wonder if the way the question was asked, that's a function of that.
Yeah.
Because 55, 60, 65, 70, 76. 76, they might have also collapsed things. That'd be surprising with a single number. But yeah, that's an odd result. I have to dig into it more. rpart doesn't worry too much about linear relationships in its continuous variables. When it looks at continuous variables, it checks the split at each individual one. So the fact that this is 76, it could be 100. It could be 100 or 1,000 or 1,000,000. Sorry, just 1 second.
Jacob used to listen to that exact song over and over again.
You know all the tunes, Dan.
We had a little tumble. Yeah, so like it would check like less than or equal to 4 versus greater than 4. So it'd split the data here, then here, then here. So between 70 and 76, these are just you can kind of think it treats all variables as ordinal rather than continuous, and that it splits them at successive values. So the fact this is 76, if this was just 71 plus, it would have the same effect. But from a data perspective, it is a little confusing. So yeah, the idea with the dot notation is it does, if we go back to the data set, it's going to predict high blood pressure with all the other variables. So this dot is the equivalent of doing HA plus CHD plus stroke plus asthma, et cetera, et cetera, et cetera. And then you just pass it the data set. So when I run it, runs pretty quick. And then when you print it, it just gives you a text version of the tree. So we can see that we start at the root, and then each row is what defines the split. So the second node is people with arthritis, the third node is people without arthritis, and then etc. It's not the easiest thing to learn, but then a text version of the tree is never going to be that straightforward. When you do the summary of the data, it's the same thing. Oh, I selected something. It's the same idea, only just way more information at each node. So you can see that. So we started this node number 1. it where's it show? So this is the split we picked, and then it shows us what the other candidate splits were. So arthritis was picked because it improved things 165 points. Diabetes was next at 134. CHD was next at 95. Doctor visits less than 2.5 was at 78. Heart attacks at 63. So you can see this is kind of the ranking of what the best splits were. And then we go down at that second node. Oops. At this second node, it stopped and there was no continuing. So the summary gives you a lot of information. So the only part that's important beyond the traditional formula data set is this control object. What the control object is it's a list of arguments that you can pass to control the construction of the tree. The three that are most important, the one that's most important is the complexity parameter. Bin bucket and bin split are how many observations have to be in a node for you to consider creating it, and then how many observations have to be in a node for you to consider splitting it. So I think, like, if you made these 10 and 20 would be more reasonable numbers. That would say don't create a node if fewer than 10 subjects get there, and don't split a node if there are fewer than 20 subjects in it. And the idea there is to just not build really specific nodes, right? You want a certain number of people getting there, otherwise you're targeting too much. When I do min bucket 0, min split 0, it gives me basically as big a tree as possible. If anyone's there, I mean, I guess I could probably set this to 2 and it would have the same effect. But the other argument, and the most important one, is this complexity parameter. What the complexity parameter says, without getting into it in too much detail, is it's a number on 0 to 1 that says how much improvement do you want from a split, right? So you have a measure of purity. It's calculated, I think the default in rpart is called the Gini index, a measure of purity at that node. And then it splits it to child nodes that each have their own measure of purity. You would hope that the child nodes are more pure, whatever that means, right? So more homogeneous, either more yeses or more nos. You want the complexity parameter controls how big an improvement was it in that split. And you can think of it kind of as a percentage. It's a proportion, right? It's a 0 to 1. The smaller the number, the bigger your tree, because that's like when we set it to 0.0041, that's about a 0.4%, like just under 0.5% improvement. We set it to 0, that's like do any split. So this mod cart 02 is going to be as big a tree as you could possibly build, where it will count any split that remotely increases things. So where mod.cart01 had like 3 splits, mod.cart02 would have, well, what do we get up to? 1,000 nodes, right? It's a huge, obnoxiously big tree. Doesn't mean anything, right? Because it's so specifically targeted to that data set. So if you do, when you run print CP, so this is that giant tree we just built. So let's show up a little, might show up a little better. Yeah, here it is in the code. What this shows us is that for each complexity parameter, it shows you the number of splits, relative error, the cross-validated error, and the cross-validated standard deviation. And it's this X error that we care about, because that's a cross. They do cross-validation within the construction of the tree, and the X error is what the cross-validated error rate is going to be at this level of the tree. So this is, you can see the relative error always gets smaller as the tree gets bigger, right? The relative error is just improvement. So at our largest tree, we have an error of 60%. I think these are percentages. But the cross-validated error, you can see it plateaus here. This looks like it. This is the lowest cross-validated error. Afterwards, it goes up. So rather than trying to decipher this, what we tend to do is use the plot. So there's a function called plot CP on the model. LAS equals 2 makes all the axis labels perpendicular to the axis. So this makes these labels and these labels vertical, just easier to read. So here, this dot, I hate these trees sometimes. this dot, one of these two dots is the lowest. I think it's probably this one. So what we tend to do is, because that error itself had a standard deviation, we take that error, we calculate a confidence interval around it, and go to the upper bound of the confidence interval. That upper bound is what we think the largest, we think that is the smallest reasonable cross-validated error we should expect from this tree. So we go up to that point, then we read over to the left and find the first tree that has a cross-validated error below it, because everything below this line essentially falls within the same range of cross-validated errors. So, which means that they're more or less, they're essentially equivalent in terms of their accuracy. So if I have, so this has 1, 2, 3, 4, 5, 6 trees with equivalent accuracies, and they have nodes 9, 12, 14, 17, 24, 28. So if I have a choice between a 9 node tree and a 28 node tree, and they both have essentially the same accuracy, I'm going to pick the 9 node tree, right? The smaller tree is just a lot easier to understand. So I take that point. It has a CP of 0.0041. So this is what I'm going to use. The 0.0041 is what I'm going to use as my complexity parameter for constructing my tree. So if we do that,
Sorry, Sam,
yeah.
does that mean is this like a roundabout way of forcing it to have the other values, like number of splits and nodes that create that tree? Like, are you saying make this tree when you do that? Or are you saying make some tree, but this is the parameter that has to be true?
So there is not a random component to building the tree. So once you determine the complexity parameter, you should get the same tree every time. So yeah, once if I were to run this, your CP, the cross-validated error will change slightly. So one thing you'll notice is, I guess I should have mentioned this at the beginning. My code starts with I have a set seed right here. And the reason I do that is because there's a lot of randomness in machine learning algorithms in places that sometimes you don't expect, like that cross-validated error. So one thing you'll find is if you keep running this, if you run this tree a bunch of times, sometimes this tree, the tree at 7 nodes, this value will pop down a little bit and all of a sudden it'll be under the line. So it's the best tree. So there's actually a bit of, it's close whether there's 7 tree or a 9 tree, a 9 node model is better for this data set. In general, I would suggest setting your seed at the, oh.
We had a good run. That sounds like a big one. Oh, coming down.
Want to say hi to everybody?
Yeah, she does. You can see right above the tree here that Sam has been Googling his own name. That's not because he wanted to. We were comparing our own names. For the people on the video, we were comparing the popularity of our own names on Google.
Say hi.
Hi. No.
That's Papa, yeah.
Everything okay there, Sam?
Did you say hi?
Hello. Do we need to call it for today, Sam, or?
I'll sit you on the ground this time.
Oh, okay.
Maybe he doesn't hear.
Yeah, I don't think he's got his headphones on.
Mm.
He said he'll put her on the ground this time. I guess she was on the top of a ladder or something.
I think among us, Dan is more in tune with the, baby crying, what that means.
All right, I'm back.
Are you
Sam,
okay?
do you need to go?
No,
Yeah.
she's all settled. It was ambitious of me to put her on a twirly chair. That was probably my mistake. She took a little tumble there.
Oh, I videotaped all of this. You're done. You're done.
But she's yeah. Oh no, I'm recording this. Figure out how to edit these things. No, she's okay. I just scared her. She landed pretty flat. You're okay, aren't you? She's back into her little videos. I completely lost my. Oh, so we were talking about so picking the final tree. So once you pick the optimal CP value, the min split and min bucket values don't really matter that much. Like they're more just for controlling your time more than anything else. So I would say pick them at a I like putting them at 0 and 1, 0 and 2 if I think the data is small enough for it. But if you do that and it's slow, bump them up to 10 and 20 and you'll get essentially the same results. You don't need them lower than that. So once we've found the optimal value, so this is the model I'm using. The big advantage of classification trees is the plotting. So that's the big advantage CART has over the other algorithms is there's a little bit of explanation to these trees. Unfortunately, it's a very old function, so this is kind of a really bad way to present things. There is an advantage here. So the y-axis actually matters here. It shows the drop shows the improvement. It's related to that Gini index value. So the move from here to here shows that there was a significant improvement. This tree looks different. What's going on here? Bought the right tree? Huh. That's how I thought the tree would look like. All right, that's fine. So luckily there's a function from the the Rattle library that produces a pretty plot. The y-axis doesn't mean anything anymore, but nobody really uses that, even though like technically the height here matters. In reality, nobody uses it. So we might as well just spread things out. The nice thing about this is that it presents a lot of information at once. So you can control these. These are the default values, but you can change them if you want to make it a little more informative. So the first line is what the algorithm is classifying the objects as. And it tends to do it, I think, just based on whichever class is more prominent. So here we can see it's starting with a no. The second line is the proportions of each class. So a lot of the stuff you'll see seems a little bit overkill because we're doing a binary outcome, but the same algorithm is used for non-binary outcomes. So if you wanted to predict like 1 of 4 types of diabetes or 1 of 4 types of something, you would have the same result, only you would have 4 cells here rather than 2. This is just the percentage of yeses, the percentage of nos. And it colors the box based on which one. So greens, in this case, greens are yeses, blues are no, and the intensity of the color relates to how accurate it is. So you can see that people with arthritis, without diabetes, with coronary heart disease, have 84% of them that end up here are yeses, only 16% are nos. The other thing, the last number is the proportion of the initial sample that ended up here. So 5% of the initial sample ends up at this node. And you can see that what's kind of happening is that we're filtering on specific disease conditions. And if you follow the no line down, so no to arthritis, no to diabetes, no to coronary heart disease, 63% of the people end up in that group, and they have a 74% no rate. So I really like the, yeah, go ahead.
Sorry. So a question. So maybe this is not so much of how to do it, but I need to understand what's going on. These classifications are based on is it the same as when in stats we talk about the discriminatory accuracy? So there, that is the beta coefficient is the mean of that variable, how that associate with the mean of the dependent variable, but then that doesn't predict. So it doesn't necessarily classify people how likely that person to have that outcome, because there's an underlying distribution. So in order to assess that, there's a discriminatory accuracy people talk about. So is it the similar idea that how better to classify? And so that's one question. The other, should I stop here and talk about that?
Oh, keep going. I want to.
Okay.
That's a good question, but I just want to think about it a little bit.
And the other question is, when you go down like these trees, I'm trying to see what's the, like, if you write out the equation, is it so then the first to the second boxes moving, is it should we think about like addition or the multiplicative? So is it almost like an interaction terms?
More like addition. So it's a partitioning. So you can actually, there are, I can't remember what the algorithm is. There are ways to turn this into decision rules. So you could say like, because one thing you'll notice is like this one says if you have arthritis and you have diabetes, you have a 79% chance. If you don't have arthritis and you have diabetes, you have a 65% chance, right? So you could combine those into a single rule where like, so there are a bunch of those like that. So there are, you can see that like amongst, after the first two, this is something that doesn't always happen, but in the arthritis group, the first two splits are on diabetes and coronary heart disease. And the second two, the splits are diabetes and coronary heart disease, right? And arthritis, yes, no, goes to, like, the yeses on these two both go to yeses here and go to yeses here. But amongst the diabetics or the non-diabetics coronary heart disease patients, the percentages are higher than if they are in the diabetes coronary heart disease. So there are ways to translate this into a bunch of like if rules to help you write it out. The challenge is at what point the rules can get very complicated very quickly, but sometimes it is like you can take a decision tree and work it out to some really clean decision rules.
Okay.
So then the final thing we'll talk about is evaluation. This also applies, I think everything we do here would work with logistic regression as well. So when we run predict on a model and pass it a new data set, we end up with the predicted, in this case, probabilities. You can, I think if you look at the predict function takes a type argument. And when you're doing prediction in logistic regression, I can't remember which one's the default. You want to do type equals prob and not type equals link, because if you do type equals link, it'll give you the logit transform of the probability, right? It'll give you the difference is, do you just want the sum of the beta coefficients and the x's, or do you want it exponentiated to get a probability? But regardless, we can get predicted probabilities for each subject. So this tells me that subject 5421 has a predicted probability of about 25% chance of being yes, 74% chance of being no. It wasn't a great sample to take because all of these people are have the same probability, and that's because 63% of people end up at this node. So 63% of people are going to end up with the same predicted probability. One of the challenges with CART trees that people sometimes miss is that we only have 2, 4, 6, 8, 9 predicted probabilities here. So there are 9. Our test set has, I can't remember how big it is. Our test set has 2,000 observations in it, but it only has 9 distinct probability values, because that's what we ended up with. Where if we did this as logistic regression, it would probably be, well, it wouldn't be that much bigger, because they're mostly binary predictors. Doctor visits being continuous would change it significantly in a logistic regression. But regardless, one thing just with CART is that, again, because it's designed for multi-level outcomes. When you predict the probabilities, it gives you a yes column and a no column. Obviously, we don't need both of those. I could infer what the no probability is from the yes probability. So you have to remember to take this, just to take the first column. Otherwise, otherwise your code will just fail and you'll forget and you'll go back and fix it. It's hard to make a huge mistake here, but you should make sure that the big thing here, much like with GLM, make sure you're pulling the right column and that it's labeling the right thing. So you want to make sure you're getting the probabilities of yes and not the probabilities of no. But you would probably detect that problem later. So once we have those predicted probabilities and we have the training set has the ones and zeros of the actual probabilities, we can build a ROC curve. And I didn't talk about ROC curves with logistic regression, but maybe I should have, because the AUC is a useful statistic for logistic regression. So there are two libraries in R that are useful here, PROC and Rocker. Rocker is a little bit more multifaceted. It has a little bit more power. It has more flexibility. It's implemented more algorithms and more complex. That being said, very few people use that. And Rocker implements what's called S4 objects, which is a different way of referencing objects in R that I just don't like getting into. It uses @ signs rather than $signs, and it's harder to dig into the results. I like PROC more because it fits more within our flow, and it gives us all the stuff we want. So you can see that I pass it two values. So I pass it, the first value is the 1, 0 column, right? These are the actual observed values. The second argument is the predicted probabilities. I set CI to true. I just wanted to report the confidence interval on the area under the curve. And that's not the default. You also don't have to pass it the levels, but I want to make sure it knows that yes is the outcome and no is the control. But regardless, once I run it, I get, oh, did I get it wrong anyway? Anyway, I don't care that much about that. It gives me an area under the curve of 70% and a confidence interval on that. Something that's useful if I run the coordinates command, it gives me the actual ROC table. So I don't know how much you remember about ROC tables, but the way they work is that for every individual cut value, predicted probability, we say, what if we split the data such that everything above this is a case and everything below it is a control, and then calculate the sensitivity and specificity on that split. The trees we're working with are using 50% as the split, right? If your predicted probability is more than 50%, yes, you get a yes, otherwise you get a no. But that's not always the best case, particularly in rare event classification. So it's worth investigating other possible split values. So we can plot the ROC curve, and this is what the ROC curve looks like. The diagonal is the random limit. So one thing to remember about a ROC curve is that it can't go below the diagonal. If it goes below the diagonal, there's like a 99% chance you just made a mistake. The mistake is almost always that you passed this variable wrong or you pulled the wrong probability. So if your curve is going under, that means you're doing worse than random. So you probably just inverted your probabilities. I've never seen a ROC curve under random that wasn't a programming mistake. I'm not saying it doesn't happen. I've just never seen it. One of the things I like about this plot function, you guys might see this if you run it in your console, is if you try and run this with a weirdly shaped, a non-square figure, I don't know how it does it, but it forces it to only use the square portion, which is really useful because ROC curves should always be presented square. The y-axis and the x-axis should always be the same size because we want 1 unit of, in this case, 0.2 units of specificity to be the same as 0.2 units of sensitivity. The other thing is that the best cut point is the point that's closest to this point up here, right? It's one of these two. I actually don't, probably this one. We want it to be closest to right here. So I think it's this point. So whatever generated this combination of sensitivity and specificity is the best. And rather than trying to eyeball it, when we run that coordinates command, if we just say x equals best, and I have no idea what x is, that's just bad programming on their part, but it works. So I'll take it. That gives us the optimal cut point. So what we see is that, yes. values yet? I was running it from the beginning again. There. So if we run op.cart01, it tells us the best cut point is the probability of 33%. So everything above, every subject with a predicted probability greater than 34%, we're going to call a yes. Everything under 34%, we're going to call a no. And using that, we get this vector. So this is just a vector of true false. Is that are we going to predict this person has high blood pressure, yes or no? So once we have those predicted values, we can compare them to the actual values in a 2x2 table. And I don't think I actually printed that.
Excuse me, Sam.
Mm-hmm.
Do you use this method for other types of classification
Yeah,
algorithms too?
All of this applies to essentially all forms of classification.
Yeah, okay. It kind of looks like, I don't know if it's exactly the same, but it kind of looks like the elbow method. I don't know if you. I forgot exactly. I used it before, but then I only used it once, so I kind of forgot how it.
So we used the elbow method for clustering. Is that what you're thinking of?
Yeah. That's what I was thinking. Yeah.
Huh. They are. Yeah, they're kind of similar. So yeah, the elbow method is the idea of the elbow method is that once the elbow method is probably more related to the CP plot, where once we stop seeing improvement in the tree, we use the smallest tree possible.
Oh,
but
yeah.
I can see that.
Sense.
Yeah, if I had another lecture, we'd probably go over clustering. Would be the next lecture we would do. So here we can see that so here I have my columns as the predicted values, my rows are the true values, and we can see that of the true no's, I predicted 984 of them as what's the command? Margins. Tab.cart. There we go. So of the 803 people that actually have high blood pressure, I correctly classified 480 of them, incorrect on 319. Of the 1,300 people that don't have high blood pressure, I correctly classified 984 and missed on 332. So I have a function here called get accuracy. This is a great example of one of those homemade functions that I don't like sharing with people because it kind of sucks, but it's useful for my own purposes. It very much, and when I was preparing these slides last night, I was having trouble with it. It's because I entered the table wrong. It expects a very specific table. It expects a table where your first row is the true yeses, your second row is the true no's, your first column is the predicted yeses, your second column is the predicted no's. It has to be in that format. Otherwise, it won't work. It'll work. It just won't produce the right things, because you can see all it does is it pulls the four values, so the true positives, the false positives, the true negatives, the false negatives, the positives, and the negatives, and then it just calculates several of the common accuracy measures we use and prints them out. So it's really useful for quickly getting the sensitivity and the specificity. But if you don't feed it in right, if you transpose one of the rows, or what I was doing is I actually had the entire table flipped where I had the true values as columns. It doesn't know that. It just sees a 2x2 table and calculates numbers off that table. But once you learn how the values go in, it is useful for quickly getting the sensitivity and specificity, overall accuracy, precision, and then the F statistics. So F1 is the one you should use most of the time, and then F2 and 0.05 if there's a difference between sensitivity and precision. So with that, I think it's a good chance for you guys to try it. So I want you to pull the Framingham data, and we're going to try and predict smoking. So I guess I didn't need to set the seed there. So we're going to try and predict smoking with whatever variables you want. So I guess I'll split you into two groups since there are 10 of you. Yeah, so I'm going to split you into two groups, and then just try and build a tree out of any variables you want. Notice that I forgot when I picked current smoke as the outcome variable. There is one variable that predicts smoking very well, and that's the number of cigarettes you smoke per day. So I had to drop that variable. Don't use that one, but any of the other variables, try and predict smoking status accurately. And we'll spend half an hour or so, I'll pop into other rooms, and then we'll all come back. All right, so where did my breakout rooms go? All right, so I'll pop into the rooms in a minute. Who's that?
I'm gonna check this quickly.
She has lost interest in YouTube, which is an hour and a half's a long time for her, even with how entertaining that is.
That's a long time. Not weird entertainment. Oh,
Yeah. I mean, honestly, it's probably the little video of herself in the corner that's the entertainment. But so how did we do? Did you guys, anyone get a tree that I didn't actually check what my final tree looked like. So yeah, so anyone get a tree that did some decent prediction?
I don't know about decent, but
But you got a final tree. So what variables did you end up including?
Yeah, we didn't do a lot. We basically did we switched the factor thing, and then we didn't get anything from there. So we just did sex, age, BMI, and hypertension. It's only 4.
I think you probably nailed it. So one thing that's interesting. So yeah, if you went through the process, you probably would have ended up with the same tree I did. But I'll show you what I did.
Okay.
Oh, I see what happened there. Okay. Yeah, so you can see that these two were just, I was doing this with Yukiko's group just to kind of explore, like I predicted smoking just with BMI and blood pressure just to see what it looked like. And then for my final model, I just fed everything in. One of the nice things about classification trees, it's a blessing and a curse. Classification trees are fairly immune to extra predictors. It just ignores them. So if you have low quality predictors, because you can see that like I fed in all these variables, but if you look at my tree on the right, it only used 3 of them. So it will only, one of the problems with classification trees is that it's kind of an all or nothing thing. Like it'll only use the most useful variables. It won't use variables that are marginal. So I fed in a bunch of variables, but if I'd fed in a model that just had sex, age, and BMI, I would have ended up with essentially the same tree. But that being said, it's classification trees are, like I said, they are fairly immune to noise, so you don't have to worry about, you don't run into the same kind of sample size issues you do with regression models. I mean, small sample sizes can be a problem because if you have a variable that has spurious relationships, that might still pop up. But yeah, so once I fit a model with a very low CP value. I tried, this is a good example of, if I set CP to 0 here, it builds a gigantic tree because I fed so many predictors into it. It just keeps going. So if you set this to 0 and then plot the CP, you get an unreadable figure. So I set my CP low, but not so low that it's going to include all splits. Like this is what, like 1/100%. Like that's a pretty low number. And so when I plot my CP for this one, this is what it looks like. So you can see that pretty quickly, my optimal points are one of these two, and this is the smallest tree that falls below the line. So I picked this one? No, I picked this one. It's changed again. This is another example of where I said the slight randomness can be a challenge, where before this point was above the line, so it wasn't as good. So I picked this tree, which is, it's only 5 nodes. It's not great. So I pruned it back to get my new tree, and then I just did what I did with the evaluation. So I got my predictions, got my rock curve, and I just stopped there. I got my area under the curve. I didn't. I guess I could have plotted it. So there's my rock. This is what I was talking about, where like even if you try and show the graph with uneven axes, it'll trick it into making sure X and Y are equal. And then this is what my final tree looked like. So yeah, so then the next thing would be to go back to that rock curve, get the optimal cut points one of these two, and then build my 2x2 table and go from there. But yeah, that's it. So there's that's about it for classification trees. You can't take it a ton farther. If you look at the place you can do most manipulation is rpart.control. I think that's the name of the function. Yeah. So if you pop that out, this tells you kind of all the other arguments, like how much cross-validation to do. So if you want your X errors to be more consistent, increase the number of cross-validations. The problem is that if I bump this up to 100, it's going to be 10 times slower. So just be cautious that you could probably get away. Like I bet you it won't be too slow if I were to do xval equals 100. Yeah, you can see it's noticeably slower, especially for this tree because this tree had so many splits. But there we go, it finished. So not the end of the world. So you can manipulate the tree, a bunch of the tree building components that way, and cross-validation value. And the other thing you can pass here, is it part of the main function? Cost? Is cost the function? I can't see where it is. So you could build custom split evaluations. So I don't know if any of you know Mo Abdelel has a cross appointment to radiology. His master's thesis was classification trees for longitudinal outcomes. So he has a when I was my first academic position after my master's, during my master's, my internship, we wrote an R library called long rpart that does the same classification, but at each node, what it does is it builds a mixed effects model and then evaluates how accurate the mixed effects model is. And the idea is you can stratify people based on longitudinal trajectories, and it only works okay. But it works great on his thesis data, and I've tried it a couple times since, and it's never found super satisfactory responses. But it's a neat idea. But you can, that idea of splitting from one node to child nodes. What we want is we want to increase the purity. We want the observations at each child node to be more homogeneous, but homogeneity can be measured in whatever way you want. The rpart function, I can't see the arguments here. I can't remember what they are. You can pass custom homogeneity functions, so you can evaluate homogeneity however you want. That being said, the Gini index or the mean squared error is how they handle it for continuous outcomes is correct 99% of the time. But yeah, that's it. And I guess this is the last one. So thanks everybody. It's been fun. I've enjoyed it. We'll take a little break here. I might do something again during the summer. We'll see. I mean, we'll see how long it is before Ava can get back into daycare. As you can see, it's a little hectic here right now. But I wouldn't be surprised if there's an announcement today about daycares shutting down. So and we might do something later in the summer, might do something in the fall. We'll see how it goes. But thanks for coming. And if you need, if you have any questions, and particularly like I said, I was going to do XML and JSON today, and it just seemed like too much. So if you have a project that needs to use XML or JSON data, send me an email, and I can share some resources I have from one of my other courses that I've done that kind of parsing in. Or if you're trying to do web scraping as well, I've done a little bit of web work, though mostly with XML. I haven't parsed HTML much. But if you have those kind of data projects, let me know, and I can help you out one-on-one. That's probably easier than trying to teach it in a group.
Yeah.
But yeah, other than that, thanks. And once we're back in the department, I'm sure I'll see you around. Well, maybe not for my New Brunswick colleagues.
Thank you so